So, as you guys know, we have been studying stoichiometry, so we should probably do a real-world scenario of how we use stoichiometry in the chemistry lab.
Yeah.
All right, so today we are going to burn magnesium oxide, or we're going to burn magnesium to get magnesium oxide. So magnesium is a metal, as you guys know. It's an alkaline earth metal, right, in the second column of the periodic table. And it comes in these little strips. I mean, it comes in lots of different forms, but one form is in these little metal strips. And if I find the end of it, there it is. So these little metal strips, right? And we're going to burn one of these guys and produce magnesium oxide. We're going to predict how much we should get and then find out how well we did, okay? So first things first, what is our symbol for magnesium?
Mg.
Mg. And if we're going to burn something, what do we need to burn?
Fire.
We need fire. We need oxygen, right? All right. Oxygen. So we're going to make magnesium oxide. Let's figure out the formula for magnesium oxide. What charge does magnesium want to have as an ion?
Positive.
Positive what?
2.
2, right? Remember, it's in the second column, so it has 2 valence electrons, and it's easier for it to lose 2 than to gain 5. So magnesium is going to have a +2 charge. Oxygen, what charge does it want to have? -2, because it has 6 valence electrons, and it needs 2 more to get to 8, so it is going to gain 2, which will give it a -2 charge because electrons, of course, are negative. So we have a +2 and a -2, and our compounds have to add up to 0 to be neutral. So what's 2 plus 2 minus 2? 0. So we just need one of each, right?
Yeah.
So our compound for magnesium oxide is MgO. So we're going to produce MgO, right? Okay, since this reaction takes a little bit, let's get it started and then we'll continue with our calculation. So I've taken a strip of magnesium and I've curled it so it will fit into our crucible. Crucible is a clay container. Clay, we like clay for heating stuff up because it dissipates heat throughout evenly. So we're going to zero out our scale so we can take into consideration the amount of the crucible, and we just want the weight of the magnesium. So we throw our magnesium in there, and we are going to start with 0.39 grams of magnesium. So that's going to be important in our calculation. And we're going to stick our crucible on a clay triangle. Clay, again, for the same reason, it dissipates heat. It will help it heat evenly throughout. Goggles, right? Safety goggles always. Hair tied back because it's heat, fire. As much as some of you probably want me to catch on fire, we're not going to do it. All right, we got natural gas turned on. Start our fire. You remember we've worked with Bunsen burners before, but what's the hottest part of the flame? The blue tip, the inner cone of the blue tip of the inner cone. So we got the blue tip right on the bottom of it, and you should start seeing it turn like an orange, a pinkish orange, and that means our heat is being dissipated throughout. So we're going to let that cook. And just so you know what magnesium looks like as we're cooking it, so what it looks like in there, we'll light a piece of magnesium on fire. Now magnesium is used in fireworks, sparklers, burns really, really bright. It's sometimes in like camping matches, flares, stuff like that. So don't look directly at it. Okay, don't look directly at it, like the sun, don't look directly at it. Look from the side, your peripheral. Okay, because if not, you're going to see nice black spots for the rest of the day. You don't want to do that. So we're going to light it on fire here.
Just look at it.
Don't look at it, food.
Oh! Oh my God!
Don't look at it.
I looked at it.
So that's what we got going on
Oh my
inside the
God.
crucible? Don't look at it. Don't look at it.
Yeah. I can see like a bright
I'll just like,
light.
you're gonna get black spots later.
Really?
Yeah.
We're gonna go blind now. Yeah.
Go blind.
2020.
And I'm much longer. All right, so that's what the magnesium looks like inside the pot. And let's just make sure, we'll take off the cover here for a second. They won't break it. And it's just now starting to get warmed up, so we'll keep it covered and do our calculations. So, remember for our Stoich problems, the first thing we have to do is write the reaction, balance the reaction, determine what our problem actually is, and then solve our problem. So we've already predicted our products. Right here, we predicted our products. So the next step is what? Balance it. And what do we have to do to balance it? Make a
T-chart.
T-chart. So what's our first element on the left?
MG.
Mg. We'll go down here. Mg. And how many mg's, whoops, what's our second element?
Oh.
O. And we want them on the same order on our product side, MgO. And how many magnesiums do we have on our reactant side? One. How many oxygens? Two. And why do we know that oxygen comes in two? It's a diatomic. It's one of the 7 guys that come naturally as a pair. Magnesium, how many magnesiums do we have on the right? One. And how many oxygens? One. Okay. So what is not balanced? Oxygen. And why is it important to balance it? So it's even. Why does it need to be even? What's that law? Conservation of mass. Mass can't be created or destroyed, so if we start with it, we better end with it, right? Okay, so we need 2 oxygens, like you said. How are we going to get 2 oxygens on the right? We're going to put a 2 in front of MgO. And as you guys know, we can't put it behind because then we change what our compound actually is. So, how many, we added a number in front. We got to recount how many Mg's do we have now? 2. How many oxygens do we have now? 2. Are we equal? No. What's messed up? Mg on the left, on the reactant. So how are we going to fix Mg? Add a 2 where?
In front.
In front of?
Mg.
Mg. Okay, how many magnesiums do we have? 2. And how many oxygens do we have? 2. Are we equal? Yes, we have a balanced chemical reaction. Go team, go. Okay. So can you guys start to see the orange on there now?
I can hear like bubbles.
That's the air, not bubbles, but yes. Okay. All right, so how much, now we're going to do our Stoich problem. Let's determine what we're actually calculating. How much magnesium are we starting with? 0.39 grams, right? We put 0.39 grams of magnesium into our crucible. And what do we want to calculate? Right, how much magnesium oxide we should get when we're absolutely done with our reaction. Yeah? So I'm going to write this down now that we have it written. Okay, let's check here. Make sure we're doing okay. All right, you guys see the flashes?
Yeah.
All right, that's it, lighting on fire. I'm going to blow a little bit into it. Why do I need to blow into it? Oxygen, because we need the oxygen, right?
Yes.
All right, so we'll add a little bit of oxygen into it. Keep that going. Okay, so for our mass-to-mass Stoich problems, we have to go from grams to moles to moles, and moles to grams. Okay, because we can't compare grams of 2 things. Just like we can't compare 5 grams of mice with 5 grams of elephants, then we'll have partial mice and partial elephants, and that just gets messy, right? So we want to compare numbers of mice and numbers of elements, just like we want to compare numbers of magnesium with numbers of magnesium oxide. Yeah? Okay, so what number do we start with? 0.39 grams, right? Grams of what? Magnesium. So we have 0.39 grams of magnesium. And we're going to go grams to moles. And what do? We bring the label down, and then we have a G, which tells us to
Go to the periodic table.
go to the periodic table and get the mass. So we have magnesium over here. How much does magnesium weigh?
24.3.
Right, so it weighs 24.3 grams per what?
Per mole.
Right, per 1 mole. So for every 24.3 grams of magnesium, we get 1 mole of magnesium. Okay, and since we divide by our labels, these guys cancel out. Now we're in moles of magnesium. Is that the unit that we're asked for?
No.
No, God bless you. No, so we got to switch from moles of magnesium to moles of magnesium oxide, right? So we want to get rid of moles of magnesium, so what are we going to do?
Bring the label.
Bring the label down. And to go from 1 mole of something to 1 mole of another, we have to use our balanced chemical reaction, right? So how many moles of magnesium do we need? 2. And for every 2 moles of magnesium, how many moles of magnesium oxide do we get? 2. Okay, our moles of magnesium canceled. Now, does my scale measure moles of magnesium oxide? No, it only measures grams. So we got to switch this guy from moles to grams. So what label goes on bottom? Moles of magnesium oxide. And how do we get grams of magnesium oxide? Go to the periodic table, right? So let's find the molar mass of magnesium oxide. What's our first element?
Mg.
Mg. And how much does an Mg weigh?
24.4.
Right, and we only have 1 of them, so 24 point, what did we say, 3?
Yeah.
And 1 times 24.3 is?
24.3.
24.3. And what's our second element? Oxygen. And how many oxygens do we have?
1.
1. And each one weighs?
16.
And 1 times 16 is?
16.
16. All right, and 24.3 plus
40.3.
16. Oh, look at us. What did you say, 40.3?
Yeah.
And remember that's grams per 1 mole. So what number goes with our mole?
1.
1, and then 1 mole is equal to
40.3.
40.3 grams of magnesium oxide. So our moles cancel. Now, are we in the unit and compound that we're asked for?
Yes.
Yes. So remember, this is just a condensed fraction, so we multiply what's on top and divide by what's on bottom. Anybody got a calculator out for me?
Yeah. 29.
0.65.
0.65? Is that what you said?
Yeah.
0.65. And 0.65 what?
Grams
Of
Magnesium oxide.
right. Remember that magnesium oxide is important because we don't know if you're talking about grams of bunnies, grams of flamingos, grams of carbon, whatever, right? We gotta have the magnesium oxide. Okay, let's see how we're doing. So in a perfect world, we would get 0.65 grams of magnesium oxide, right?
Yes.
Okay, let's add a little more oxygen. We're really close. How am I going to know when it's done?
Start boiling.
It's going to what?
Make light.
It's not going to make any more light. Because the no, you're good. Because the magnesium is what burns bright. Magnesium oxide is just like a white powder. It's like that on the side there. That's magnesium oxide.
Oh, I was watching a movie yesterday.
So we're really close. Again, don't put your face over fire like this. But we need more oxygen in there, so we'll take the risk.
I'll be at your funeral.
It's one of those do as I say, not as I do things, you know, that adults do all the time.
Certified in first aid CPR.
Yeah, well, see, I'm good then. All right, and I'm gonna kind of crunch it down in here to make sure we get as much burnt as possible. So that was a little bit of magnesium that's not quite converted yet.
Whoa, That's awesome.
Yeah, it was on the bottom, so it wasn't getting as much oxygen. So now that it's exposed to the oxygen, it's burning a little bit more.
Oh.
Okay.
My heart like skipped a beat. It's like,
All right, so I'm crunching it. Do you guys see any more bright white lights?
No.
No, it looks pretty much done.
Yeah.
All right, so let's see how we did. Oh, we got a little guy going there. Okay. All right, ready? Boom, boom, boom. And it looks just like that white, like, ooh, sorry, like the white powdery stuff. So it kind of looks like this. It looks like, you guys see that little like strip there?
Yeah.
But as soon as I touch it, it like crumbles up. That's what it looks like in there. It's just like a ashy white powder. And I'll dump it out here in a second after we weigh it so you can see what it looks like. Sounds like a crap. All right. Ooh. Okay, we got, remember, in perfect world it would be 0.65. That's called our theoretical yield, because theoretical yield, because theoretically in a perfect world we get 0.65 grams. Our experimental yield is 0.57 grams. Okay, so let's calculate how well we did. This is called a percent error calculation. Most experimental scientists do this to see how well that they actually carried out the experiment. So you take the theoretical minus the experimental divided by the theoretical, and this is actually what you do, similar to what you do when you calculate a grade on a test, times 100 because we want a percent. Did you got that calculator still?
Yeah.
And this is percent error, not percent correct. 87%? Trey got it? 87%. Wait, 87%, that's not right. It should be the opposite, which would be 13%, right?
Oh, yeah,
13%, yeah. It would be 13%, and then our percent correct, scared me for a second. Percent correct would be 87%. How many of you guys would take an 87% on a test? B plus, right? Yeah. All right. So we did this experiment 87% correctly. Yeah? So how could we have lost some material? What did I do during my experiment?
Hello.
I blew on it, right? What happens when you blow down onto something?
Powder goes out.
It goes out, right? And if you look, there's a few little dust particles around here. That would make our weight lower. What else would make our weight lower?
Banging it with a stick.
Banging it with a stick, right? If you notice. What?
The stuff on the stick.
Yes, exactly. The glass stirring rod that I used to crush it has a little bit of particles on it. So that took out our weight right there too as well. I know. So that's probably some of it. And maybe if the reaction didn't go to completion, that would be some of it too, because magnesium weighs less than magnesium oxide. And just so you can see what it looks like. So that's what that ash looks like. Yeah?
Yeah.
So that if you do chemistry in AP, if you take AP chemistry or take chemistry in college, that is similar to a way that you would use stoichiometry in that lab.